Hello friends, in this video we prove that as function f is integrable, the mod function is also integrable. Point is that if f is bounded and integrable on closed interval a comma b, then mod of f is also bounded and integrable. So let us apply first the condition of bounded. What is given? Since f is bounded, as f is bounded on closed interval a comma b, there exists a number k such that mod of f of x is less than equal to k for all x belongs to closed interval a comma b. But this is what? This is nothing but mod f of x. Okay, so this is therefore this function mod f is also bounded and integrable, is bounded on closed interval a comma b. Again, function f is integrable. As function f is integrable, therefore there exists a partition p of closed interval a comma b such that xn equal to b, such that this upper sum minus lower sum UPF minus LPF is less than epsilon we have now. So let capital Mi comma small mi semicolon capital Mi dash comma small mi dash be the supremum and infimum of f and mod f respectively in delta xi. Let us take this. Therefore, for any 2 points x1 comma x2 belongs to this delta xi, mod f of x1 minus mod f of x2. What is this? This is nothing but mod of f of x1 minus f of x2. Okay, so let us take one more step. This is modulus value, but as it is in the modulus, this is same as mod of f of x1 minus f of x2. Okay, but we know that this is less than capital Mi minus small mi. So we get that the supremum relation mi double dash minus small mi double dash less than equal to capital Mi minus small mi. Okay, this implies that the upper sum of mod f function minus lower sum of mod f function is a less than equal to upper sum of f minus lower sum of f, which is less than epsilon. That is, upper sum of mod f function minus lower sum of mod f function is less than epsilon, and hence the function is an integrable function. Okay, now let us prove the second parts. We know that for a modulus function, f of x and minus f of x are both less than equal to mod of f of x for all x belongs to closed interval a comma b. Then we have one important deduction is that mod of f of x is less than equal to integration a to b mod of f of x. Also, as this function f is less than equal to g of x, then f of x is less than equal to g of x, then integration of f of x is less than equal to integration of g of x. We have this deduction. As f of x is less than equal to mod f of x, we get that this is less than equal to this one. Also, the minus integration of this minus integration a to b of f of x, which is nothing but integration of minus f of x, and this is less than equal to integration a to b mod f of x, right? So combine these two. This is minus and plus. Both values are less than equal to mod f of x. Therefore, we can write that modulus of integration of f of x is less than equal to integration of mod f of x. So this proves the of this theorem is on your screen. If f is in square is also integrable on closed interval a comma b. As f is integrable, it is a bounded function. Since f is a bounded, so mod f is also bounded. We have proved one theorem. As f is integrable, f is bounded, mod f is also bounded on closed interval a comma b, and there exists, as function is bounded, there exists a number k such that mod of f of x is less than equal to k for all x belongs to closed interval a comma b. Now friend, we have to show that the function f is a f square is integrable. So you can see that f square of x, mod of f square of x equal to, this is nothing but f of x, mod of f of x square, and this is less than equal to k square. So therefore f square is bounded on closed interval a comma b. Now consider let a partition P. We need a partition every time, and for this partition, suppose since function is integrable, therefore for this partition, suppose that let capital Mi comma small mi, these are the bounds of mod f. These are the bounds. Bounds means supremum and infimum of the function mod f, and capital Mi dash comma small mi dash be the supremum and infimum of the function f square. Okay, bounds means supremum and infimum of mod f respectively. Okay, now let us calculate upper sum of the, then we can take that upper sum of f square minus lower sum of f square. This is nothing but upper sum of f square. This is summation of capital Mi dash whole square minus small mi dash whole square into delta xi. I is equal to 1 to n. Okay, but what is the this relation? This is equal to less than equal to, this is less than equal to summation of, here look at this, f of x, f of square is less than equal to k square. So this is less than equal to summation of mi square minus small mi square delta xi. I is equal to 1 to n, right? But a square minus b square means a minus b and a plus b. So we have mi minus small mi into capital Mi plus small mi into delta xi. I is equal to 1 to n. But this mi is less than equal to k. All these values are less than equal to k. So we have, this is less than equal to 2k into summation of capital Mi minus small mi into delta xi. But then what is this capital Mi minus small mi? Capital Mi minus small mi is a upper sum of mod f. So we have now here, this is less than equal to 2k into upper sum of the function mod f minus lower sum of the function mod f, right? Again, f is integrable, therefore mod f is also integrable. also integrable. As mod f is integrable, for epsilon greater than 0 there exists partition P with norm mu of P less than delta, such that the upper sum minus lower sum is less than epsilon. Here we take this value is less than epsilon divided by up mod f minus lp mod f is less than epsilon divided by 2k. Okay, here you can substitute here upper sum minus lower sum. If you substitute here upper sum minus lower sum, then we have upf square minus lpf square is less than equal to 2k into epsilon divided by 2k. That is, it is less than equal to epsilon, and hence f square is integrable. F square is integrable. So this is about